All right, so our next topic is in section 2.4. We're going to talk about the second derivative. Now, I alluded to this in the previous section when we were talking about the position function, because we saw that the derivative of the position function, change in distance over change in time, is precisely our velocity. And then we took the derivative of our velocity function, which we found to be acceleration. Now, remember, the derivative of the velocity was the derivative of the position. In other words, we did take our second derivative. Okay? So, since the derivative is a function itself, we can compute its derivative, which is going to be a function itself, etc. Now, let's talk about what it means, especially graphically. Now, we're really going to be waiting to hone in on the second derivative until we get into chapter 4, where we discuss graphing. But here's what I would like to do. What I want you to do is recall the following. Okay? My first derivative is positive if and only if my function is increasing. My first derivative is negative if and only if my function is decreasing. This if and only if means that it goes both ways. The conditional goes both ways. So this gives us a relationship between the function and that function's derivative. Okay? Now, since f double prime is the derivative of f prime, we can make these same relations, okay? So now our original function is our derivative, and then its derivative is the second derivative. So what can we say there? We can say that the second derivative is positive if and only if my first derivative is increasing. And my second derivative is negative if and only if the first derivative is decreasing. Notice function, function's derivative. Function, function's derivative. Okay? Now, what does it mean, though, for our derivative to be increasing and similarly our derivatives to be decreasing? Well, what this is saying is that the slopes of the tangent lines to your original function are getting larger. And here this says that the slopes of your tangent lines are getting smaller. All right. So now what I would like to do is relate what that tells us about our original function. As you guys know, in math, a picture is worth pretty much everything. So let's talk about f prime increasing. I claim that I can draw two pictures where my derivatives are increasing. Could be this or this. Okay? Why? Okay, and this is my original function f of x. Why? Because here, let's look. Our slope is essentially 0, and as our x values are increasing, so are our slopes. Okay? In a similar manner, look, our slopes are really negative, but as our x values are getting larger, my slopes are getting closer and closer to 0. In other words, they're increasing. They're getting less negative. I claim in both of these pictures, my graph is bending up. We call that concave up. So notice, my derivative can be increasing. In other words, my second derivative can be positive when my original function is increasing, or my original function is decreasing. Okay? So notice, my function can be increasing and decreasing in both scenarios where your first derivative is increasing. Now, what does that mean for my first derivative to be decreasing? Well, I claim that my graph can look like that, or my graph can look like that. And again, this is the graph of my original function. Why is this the case? Well, look, here my slope is nearly 0, and it's getting more and more negative. My derivatives are getting smaller. And here my derivatives are positive, but notice as I'm moving over, they're getting smaller and smaller. They're approaching 0. Notice the shape of these graphs, they're bending down. We call that concave down. And again, notice a function can be concave down when your function is either decreasing or increasing. Okay? So, what can we put together with that? What we can say is as follows. When your second derivative is positive, notice your first derivative is increasing, but what does it say about our original function? It tells us about the shape of the graph. So that tells us that f prime is increasing, but it tells us that our function is concave up. And similarly, when your second derivative is negative, that tells you that your first derivative is decreasing. But to our original function, it tells us that it's concave down. So when we talk about the second derivative, what we're getting to is what's happening to the shape of the graph. All right, so let's just quickly go through a couple of examples here where we can kind of put our first derivative and second derivative into practice. So what I want you guys to have put together here is that when you're talking about your second derivative, you're talking about the shape of the graph. When you're talking about your first derivative, what you're talking about is whether your function is increasing or whether your function is decreasing. Okay? So, what if I want us to sketch a graph of a continuous function where my derivative is positive for all x and my second derivative is negative when x is less than 2, and it's positive when x is greater than 2. Okay? So let's draw a possible graph of our original function f. Well, what does it mean for our first derivative to be positive everywhere? Doesn't that mean that it's constantly increasing? So we know that this is an increasing function everywhere. However, when we're less than 2, it's an increasing function that's concave down, but once we're greater than 2, it's still increasing, but now the shape of my graph has changed to be concave up. Okay? And we can do other examples as well. What if we want to sketch a graph of a function whose first derivative is negative everywhere and whose second derivative is negative everywhere? Well, doesn't that mean that he's just a decreasing function that's always concave down? And there's one such graph. All right, I hope this helped. Thank you.